Dread and Promise, which it says confronts similar topics as those discussed in this course. It will be tomorrow morning, 18th of January, 9:30 a.m. in the Lecture Theatre 1 in the new Economics building, which is just next door. Okay, I certainly will go. I don't know if anyone else will be able to. Also, on our Saturday extra session, first I've asked to be sure that we get a student there with a hand mic, because I want to have people actually talking about these ethics problems, so we need to have a microphone. However, this room is occupied 10 to 12 on Saturday, so we will have to meet in LT1, which is this cavernous room around the corner somewhere, okay? I'll announce that every day so people remember. Now, I've put the time? 11:15 still, same time. I'm trying to make everything as similar as possible. Now, I put this up again just to remind you that this number, 5, is the atomic number, and it actually corresponds to the number of protons in the nucleus, and that defines the number of electrons around the nucleus, and that defines the chemical properties of the element. The number underneath is called the atomic mass. Now, it's not a mass in terms of kilograms. It's the relative number of particles in the nucleus. Okay, so it is this number, protons, plus the number of neutrons, 9. So the difference between those two numbers is the number of neutrons. It is a fraction because you can have isotopes, the same number of protons and varying numbers of neutrons. Okay, and so this number isn't a mass in grams, it is the relative number relative to 1 for hydrogen of the number of particles in the nucleus. Now, we're back in the beginning of 1939. Fermi won the Nobel Prize in Physics in December of '38 and went to the United States and took up a position in early '39 as professor at Columbia in New York. He had a graduate student there who also became quite well known, named Herbert Anderson. But the university had a cyclotron, a new machine that had been built in 1936. A cyclotron is one of the earliest machines used to accelerate particles. And I'll show you a picture tomorrow of one. It's not important about how they work. But it accelerates particles to higher and higher speeds. And the bigger the cyclotron is, the faster the particles can be, the greater the acceleration. And with this new energetic beam of generally protons, they could bombard beryllium and knock neutrons out, just as they had done previously with a radium source and beryllium. However, in this case, since you could change the energy of the beam, you could change the energy of the neutrons, and so they could control that, which was very interesting. And now with this cyclotron, Fermi and Anderson, working along with Leo Szilard and Walter Zinn, again, tremendously famous people, bombarded uranium with neutrons. And they showed that you did indeed get fission, which is the first product. And moreover, that extra neutrons were produced. And it is whether extra neutrons are produced and how many that determines whether fission and therefore a reactor or a bomb can be made. I will discuss this over and over again because the number of neutrons produced in fission determines whether you get a reactor or a bomb. In a reactor, as we shall see, it cannot, because of the way it's made, it cannot undergo a nuclear explosion. It can, it generates a huge amount of heat, and that heat is taken away by a coolant. And if that coolant goes away, then it gets so hot that it blows up. But that's a chemical explosion. And that, as we shall see, is peanuts compared to a nuclear explosion. It cannot explode under nuclear, and we'll get to that. Now, in uranium down here, the most common isotope is uranium-238, and that means it has 238 particles in its nucleus, and if I subtract 92 from 238, I get 146, and that's how many neutrons are in uranium. And it was thought that that's the only isotope available. But careful analysis showed that there are, in fact, several isotopes, and there was an isotope called U-235, which had 92 protons. It has to have 92 protons or it isn't uranium, but it only has 143 neutrons. That's quite different. However, that is a very rare isotope. It occurs in natural mined uranium 0.7% of the time. So it's very rare. 99.3% is U-238, 0.7% is U-235. There is also U-233 and 234, but in such small amounts that I won't bother talking about them. This work was published in the open literature, but soon physicists realized that that was not a terribly smart thing. They limited publication. In fact, from 1940 until 45, there was no work in any country that was kept as secret as the work on the uranium bomb. This kept the knowledge of what was going on in America from the Nazi Germany, but not in the least from the Soviet Union, as we shall see. They had spies inside. Now, I want to go back to Leo Szilard, this amazing man I find. Back in 1935, he was working briefly in Oxford under a fellowship from Imperial Chemical Industries, and he was trying to produce radioactive elements, not by bombarding them with neutrons, as people had done, but by bombarding them with X-rays, because X-rays are plentiful. And if you could make radioactive elements using X-rays, then you could create something like radioactive cobalt at a cost of a few dollars per gram, compared to radium down here, which was used for everything else, which cost $50,000 a gram at that time. And cobalt-60, I picked that out, is a very common radioactive element. Notice that its most common isotope is 59, but cobalt-60 is radioactive. It produces a gamma ray, which is used very commonly in medical treatment still to this day. This work of Szilard's brought him into contact with a wealthy American named Lewis Strauss. Except Strauss lived in Virginia, where people couldn't pronounce Strauss, so they called him Strauss, and so he's known as Lewis Strauss. He was a very wealthy industrialist, mostly by marrying a rich woman, but also by investing carefully. And by 1937, both of his parents had died, and he was very interested in this problems of radioactive sources. And Szilard offered to give him free use of his data if he would fund Szilard's research, which he did. And after learning of the fission results in 1935, Szilard realized that this was much more important than creating artificial radioactive elements, and so he wrote back to Strauss, who did not fund his work. the energy released in fission is close to 200 million electron volts MeV per fissioning nucleus. Now that's a hell of a hard number to understand, because an EV, an electron volt, is the amount of energy an electron gets if it's accelerated through a voltage or potential difference of 1 volt. However, I can give you a rough scale, because the most powerful chemical explosion we can create generates 5 electron volts, whereas a nucleus creates nearly 200 million electron volts. So chemistry gives us 5 units. Nuclear fission gives us nearly 200 million units, a gain of almost 40 million times. That's a big, big number. Especially when you realize how many nuclei are in something. I want to show you what is absolutely my favorite number in the world. Here I have a glass of water. Okay? How many water molecules do you think are in there? Well, you don't know. The answer is an enormous number. There are more molecules of water sitting in here than there are glasses of water in all the oceans on Earth. I go out, and this number absolutely staggers me. I go out, and I can calculate it, and I did. But I go out and I look at the Atlantic off the coast here, and I think, how many times could I dip that in? And all the oceans, all the oceans. It's an astonishing number. So if you take this tiny little 200 million number and you multiply it by this gazillions in here, you get a nuclear bomb. Now, I want to introduce the idea of a cross-section, which is very important in physics. And this was created by Rudolf Peierls, a man I was privileged to meet many years ago, another German-Jewish refugee from the Nazis. He would come to play a significant role in Los Alamos. Now, imagine I have a window, which is 1 square meter in diameter, and I throw a ball against the glass window. 1 time out of 10 throws, the window shatters. 9 times out of 10 throws, the ball bounces off. In physics terms, this would mean I have a disintegration cross-section that is breaking of 1/10 of a square meter, and an elastic cross-section, bounce off, of 9/10 of a square meter. Now, nuclear cross-sections are not measured in square meters because nuclei are incredibly small. They're measured in units of 10 to the minus 24 square centimeters. That's decimal point, 23 zeros and a 1. That's a very small number. It is so big in nuclear terms that that unit is called a barn, because it's as big as a barn. In the field I worked in when I was doing active research, the cross-sections were measured in either millionths of a barn, a micro barn, or billionths of a barn, nanobarns, which are reasonable cross-sections. But there's another number involved, which is called a capture cross-section. Imagine that the window is open, and so instead of breaking or bouncing off, the ball enters the room. Okay? So this is an additional number. So a neutron coming in can shatter the nucleus, it can bounce off the nucleus, or it can be captured by the nucleus. As I said, using accelerators rather than radioactivity as the source of neutrons, we could make measurements at different bombarding energies. Now, this is the hardest slide we have to understand. Here's U-235, here's U-238. There are 2 possibilities I want to talk about, fission and capture, okay? And up here is a number which is the cross-section. You don't care what it is. And over here is the energy. Now, for U-235, fission dominates, Okay? And fission starts at the lowest possible energies and just decreases. And it's bigger than capture by almost 10 times. For U-238, however, down here, fission doesn't start until way over here at quite a significant energy, and it's a smaller number than it is for 235. Okay, and that's really all we need to understand from this graph. These are called slow neutrons, and these are called fast neutrons. When U-238 captures a neutron and it goes to U-239, I go from 92 protons and 146 neutrons, which two even numbers, to 92 protons and 147 neutrons, an even and an odd number. That's significant. 235, 92 and 145 neutrons, 143 neutrons, I'm sorry, goes to U-236, I add one, and that gives me 92 and 144 neutrons. Even. Now, an even number of particles by a very subtle symmetry argument has an energy advantage over an odd number of particles. Okay. To fission well, when you capture a neutron inside a uranium nucleus, that some of the mass of that neutron goes into energy to glue, to stick the neutron inside. And that amount of energy is called 5.3 MeV. Okay? But to fission a nucleus takes 6 MeV. 5.3 is not big enough, less than 6. But for U-235, which has an energy advantage of 1 or 2 MeV, you get 5.3, and you get 1 or 2, that's greater than 6. So U-238 can fission, but it needs more energy of the incoming neutron to get it up over 6. Whereas any energy neutron will work fine for this even split. So U-235 will work. The key then to the question of whether a chain reaction can be generated is how many neutrons are created. So that if it's, say, 2, as I mentioned yesterday, every fissioning uranium gives you 2, which fissions 2, which gives you 4, which fissions 4, which gives you 8. People then tried to measure the number of neutrons. Joliot-Curies, who did not have a cyclotron but had lots of radium, tried to generate tried to measure the number. They got greater than 1. Fermi, with his cyclotron in New York, said, I think it's about 2. The number is really 2.3, but only 2.3 for uranium-235. The number for uranium-238 is less than 1. And that's why a reactor can't blow up, because there are not enough neutrons. A reactor is 98%, 97% U-238. There aren't enough neutrons for it to blow up. A bomb is over 90% U-235, off it goes. Okay. Now, in March '39, Hitler invaded the rest of what had once been Czechoslovakia, so he had both Czechoslovakia and Poland without firing a shot. And on the very same day, there was a meeting at Columbia with Eugene Wigner, Szilard, Fermi, and George Pegram, who was the department head. Wigner said, look, the time for amateurism is over. We need to tell the government. Pegram had contacts in Washington and in the Navy, and so he said, well, we should do that. Fermi was actually on his way to Washington. Fermi had won a Nobel Prize. He had a lot of prestige. Pegram gave him a letter to carry to the Navy. The Navy was uninterested. Moreover, while Fermi was sitting outside waiting for this meeting, he overheard a conversation inside the room where he was going, where somebody said to the admiral, there's this Italian physicist out there, except he didn't use the word Italian. He used an epithet for Italian, which Fermi heard and was greatly insulted by. There were arguments all over the physicist world. Oh, what happened to my... this is what fission looks like, okay? You have a spherical nucleus. You add one more neutron to it. This is U-235. You add a neutron, you make 236. It becomes ellipsoidal, and then it necks down in the middle, and you get baryon and krypton usually out of that, and 2.3 free neutrons. This is a letter from Teller, because Wigner, Teller, Szilard, John Wheeler, Leon Rosenfeld, all these giants of physics, were all for imposing secrecy. Bohr was against it because he said we must never have secrecy in science. He's wrong about that. Now, once the importance of U-235 was understood, the problem was separating the 0.7% of U-235 from the 99.3% of U-238. You cannot do that chemically, because chemistry depends not on the nucleus, but on the electrons. And both isotopes have 92 electrons, and they have identical chemical properties, so that doesn't work. At Yale, a Norwegian-born scientist named Lars Onsager, who later won the Nobel Prize in Chemistry, described a process of gaseous thermal diffusion, which had been invented already in Germany, where you have a tube which you heat on one side and you cool on the other side. And because the lighter atoms, when they're hot, move a little bit faster than the heavier atoms, you separate them that way. This is a majorly difficult process to do, and was thought by people like Bohr that it was impossible, just too big, too difficult. Nobody had the idea that the United States would invest billions of dollars to build a plant in Oak Ridge, Tennessee, to do exactly that. Now, in April of 1939, the French Joliot-Curie published a paper claiming 3.5 neutrons per fission. The number is 2.3. Now, Joliot was a very famous man. He had won the Nobel Prize in 1935, he and his wife Irene. And people read his articles and paid attention. In particular, G.P. Thompson, a Nobel laureate himself, and the father of a woman who lives here in Cape Town. He read this and understood its importance and realized what it could do in terms of a weapon. He contacted the British Air Ministry. More ominously, a physicist in Göttingen alerted the Reich Ministry of Education, which led to a secret conference in Berlin in April of '39, which led to a research program in Germany to a ban on uranium exports, to the provision of supplies of uranium from the Czechoslovak mines at Joachimsthal. The news also reached the Wehrmacht's Ordnance Department, which studied high explosives, and the War Office agreed research should proceed immediately. The Germans were in the game. Fermi continued to think that he could make fission in U-238 normal. I mean, after all, nobody really knew. And he was unconvinced by Bohr's arguments about 235. That made the generally mild-mannered Dane very angry. An experimental team of Fermi, Anderson, Szilard set up an experiment at Columbia to measure things, and this involved a lot of hard work. physical labor of carrying things. Szilard said, I'm not doing that. I can contribute more by thinking. Fermi, who was a very hard worker, was infuriated. So we had Bohr angry with Fermi, Fermi angry with Szilard. These geniuses acted just like school children. And I can tell you, having worked with some pretty bright people in my time, if you're working on an experiment at 2 or 3 in the morning when things aren't working well and tensions are high, words get exchanged that would not normally be used. And once or twice I have seen more than words. I have seen a fist thrown. Not against me, fortunately. Now, there are problems in creating slow neutrons, of course. Slowing them meant naturally, as I said, colliding them with something light, like throwing a cricket ball against a cricket ball rather than against a bus. So the obvious material is hydrogen. But hydrogen doesn't work because hydrogen also absorbs neutrons, and so it reduces the number that are available, and that's, that hurts the fission process. The next most useful common element is carbon. And so the question was then, would carbon work? So Szilard wanted to measure the neutron-carbon cross-section. Fermi had measured this in Rome, because he measured everything in Rome, but he didn't measure it accurately enough for this kind of work. So they needed to do an experiment. If carbon didn't work, the next best element was deuterium, heavy water. Deuterium is an isotope of hydrogen. Whoops, anyway, you've seen it. Where the one proton is stuck together with one neutron, so it's twice as heavy. It was only discovered in 1932, and it comes along with ordinary water, and separating it is a very difficult process which involves a lot of electricity. And it's more effective than carbon, but it's a heck of a lot harder to get and much, much, much more expensive. So Szilard went out to look for high purity carbon. They didn't have much money, didn't see what whether high purity carbon would work. The reason for high purity carbon is, and we're talking about graphite here, because you need lots of it. The reason for high purity carbon is if you buy an ordinary piece of graphite, it has impurities in it. And one of the major impurities is the element boron, which is the fifth element in the table. Boron is poison for neutrons. That is, it has what's called a high capture cross-section. It eats them. And so if you scatter neutrons from ordinary carbon, the boron will reduce the number. So you need high purity carbon. The problem was that Szilard realized this, and he thought, if I know it, the Germans know it, because it's nature. But really, only Fermi knew it, because only Fermi had scattered neutrons from boron and knew that it captured things. And Fermi was not any longer in Europe, because, of course, his wife and children were Jewish and subject to racial laws that Mussolini adopted in early '38. Had Fermi stayed in Rome, the world would likely be a very different place today. There's this old thing about for want of a nail, the shoe was lost, etc. For want of Enrico Fermi, Hitler never got the atomic bomb. Szilard turned to his friends Teller and Wigner for help. They were very concerned that the Belgians had the world's largest supply of uranium in their colonies in the Congo. Congo has more uranium than the rest of the world put together. What if they sold that ore to the Germans? Then Szilard realized that his old collaborator, Albert Einstein, was a close personal friend of Queen Elizabeth of Belgium, and maybe Einstein would appeal to her to prevent the sale. So Einstein was on holiday at the end of Long Island. Long Island is appropriately named. It's very long, about 250 kilometers long, and it ends in two forks separated by a large bay. Einstein was vacationing in a town called Peconic, which is on the North Fork. So on the 16th of July, 1939, Szilard and Wigner drove east. Szilard couldn't drive, so Wigner drove. That's why he needed Wigner to go. They got lost because nobody had GPS in those days. So, however, when they got to Peconic, they found this little 8-year-old. They asked him, he knew exactly where Professor Einstein lived. So they got there. Szilard told Einstein all about the work on uranium and the possibility of a chain reaction. Einstein was apparently quite astonished. And they spoke, of course, in German, and Einstein said, "Daran habe ich gar nicht gedacht," which is, I have absolutely not thought about that at all. Wigner insisted that the US government be informed, and after discussion, they decided to send a letter to the State Department with a letter to Belgium attached. A German draft was written. Szilard took it back to Princeton, had it translated to English, typed up, and then, it being summer, he drove off to California on holiday. Meanwhile, Szilard had a phone call from a friend of his, an economist, also refugee, named Gustav Stolper, who came from Austria. And he said he had discussed this entire affair with Alexander Sachs, a fellow economist. Sachs had contributed economic ideas to Franklin Roosevelt in the presidential campaign in 1932 and had remained a close confidant and advisor to Roosevelt. He talked to Szilard and convinced him that this matter was of the utmost importance, utmost seriousness, and should be addressed to the president and not to the State Department, and that he would personally carry a letter to the president. So Szilard drafted a letter to Roosevelt, and he posted it to Einstein. Wigner, of course, was gone, so Szilard got Teller to drive him out. Here are pictures somewhat later, of course. There's Eugene Wigner, and there's Teller. Notice this is much later. You can see what he's got on his wall. And here are Einstein and Szilard. This picture was not taken at the time. It was taken later for historical reasons, because this was one of the most important meetings in the history of the world. So they took that for historical purposes. A long letter was drafted and a final copy sent to Sachs finally on the 15th of April. These three Hungarians were very much aware at this early stage of what a devastating weapon they were talking about. And they hoped for more than just to deter the Germans from creating one. What they really wanted, Szilard especially, was a worldwide agreement on the non-use of nuclear weapons. Now, Hitler had signed a treaty of non-aggression with Stalin in August 23rd of 39, the so-called Molotov and Ribbentrop Pact. And then he invaded Poland on the 1st of September, the beginning of World War II. The dive bombers and tanks of the Wehrmacht were met in various places by Polish cavalry on horseback with swords and spears. It was not a very fair fight. Again, as a sign of how amazingly different the world was in those days, Roosevelt appeared to all the combatants not to bomb civilians, having been shocked by the Japanese bombing of Shanghai in '37 and by Franco's bombing of Barcelona and Guernica. We've seen numerous cases, most lately in Aleppo, where such concerns have long since disappeared. Britain and France entered the war on the 3rd of September, and Roosevelt's schedule became very busy, so Sachs didn't have a chance to speak with him until the 11th of October. Here, oh my, I don't know what happened with that, but anyway, that's a copy of Einstein's letter, which is impossible to read. Oh, yeah, I wrote this in Mac speak and then translated it into that awful stuff that Windows does, and it obviously didn't translate very well. Sorry. By the 11th of October, though, Sachs had a meeting with Roosevelt, and Sachs liked to tell stories, and so he started the discussion. Well, okay. It's readable. Yeah, I give up with this nonsense. He started the discussion by mentioning a young American inventor who wrote a letter to Napoleon, and he proposed to build a fleet of ships with no sails that could attack England in any weather. He could bring Napoleon's army to England in just a few hours without fear of wind or storm. He would bring his plans to show to the emperor. Napoleon laughed at him, at the idea of, ships without sails. This young American was named Robert Fulton. He went back to the United States with his invention of the steamboat and changed the world. On such historical accidents changed the fate of nations. Sachs then went on to describe what he had learned from Szilard and Einstein, but he gave the president an 800-word summary of his own rather than a complete Einstein's letter. Roosevelt invited him to come back the next day, and Sachs was in great turmoil during the night because he wondered if he had done enough to convince Roosevelt of the importance of what he was saying. And he needn't have worried, because the next day when Roosevelt had read him, Alex, what you are after is to see that the Nazis don't blow us up. And his response was, precisely. Meanwhile, the Germans were not idle. They called a conference of chemists and physicists before this on the 16th of September in Berlin, where they were told that German intelligence had learned of uranium research in both the US and in Britain. It wasn't hard because Bohr and John Wheeler, another genius, had published a paper in which they discussed the idea that only U-235 would work, and that was published in the open literature, so it wasn't very hard to find out. At the meeting, Otto Hahn, the German who had discovered fission, said that separation of these isotopes was difficult, if not impossible. So they called on Werner Heisenberg, then the most famous scientist living in Germany, and he said, well, it's possible to slow neutrons with a moderator, and it might be possible to separate the isotopes. The idea of layering uranium and moderator that Szilard and Fermi had was being discussed. The Nazis were in the race. The first moderator they discussed was heavy water, of course, and so they knew that ordinary hydrogen wouldn't work. In America, Roosevelt set up the Uranium Committee under the direction of the head of the National Bureau of Standards, whose name was Lyman Briggs, an old, very slow-thinking conservative man. They had a meeting set for the 21st of October, and the Hungarians were invited. Szilard outlined the whole problem to the Army and the Navy who were there, and looking for money, of course. Sachs was there. When Szilard said that he thought that a bomb equivalent to 20,000 tons of TNT could be constructed, the Army representative scoffed, and he said, look, weapons aren't that important. It takes 2 wars to see whether a weapon is useful or not. What counts is troop morale. At which point, Wigner exploded with sarcasm, and he said, oh, I always thought that weapons mattered, and I'm glad to know I was wrong, because now the Army won't, if morale works, the Army doesn't need more weapons, and Congress doesn't have to appropriate so much money, and think of all the money we can save, and on he went. The Army guy looked glummer and glummer and eventually said, well, you'll get your money. The committee recommended to the president adequate support for a thorough investigation, but nothing happened for months. Meanwhile, a chemist at the University of Minnesota undertook to separate a little bit of 235 from 238. Now, I want to go back both in time and in place to Europe in the spring of '39. Poor Lisa Meitner was isolated and unhappy in Stockholm. At that time, Otto Frisch was working in Copenhagen with Niels Bohr, and he was very worried about that the Nazis would soon be in Denmark. Of the 3 Scandinavian countries, Sweden was very neutral, although, of course, it did, to prevent invasion, it did cooperate with the Nazis during the war to some extent. Norway was very mountainous, which made invasion difficult but not impossible. Meanwhile, Denmark was completely flat. It had a border with Germany. It had lost a significant chunk of territory in the 1860s in a disastrous war with Prussia. And Frisch was deeply concerned. Then Mark Oliphant, the department head from the University of Birmingham in England, visited, and Frisch asked him for help. Oliphant invited him to come to Birmingham, which he did. 2 small suitcases and no money. He showed up in England and was given a position as an auxiliary lecturer. For the first time since his meeting with his aunt Meitner the previous Christmas, he was back in the business of fission. He didn't have a neutron source, so he couldn't do any experiments like that. So he tried to see if he could separate 235 from 238. And he used a German invention called the Clusius tube, in which you have a tube and you have a wire going down the middle. You put uranium in a gaseous form, which you can do on the inside. You heat the wire electrically. You have cold water on the outside. The light element goes up, the heavy element goes down, and you get some separation. He had a very hard time actually getting anything built because both the glassblower, whom he needed, and the machine shop were terribly occupied. Since he was considered an enemy alien, in some sense, he didn't know that what these people were completely occupied with was the building of a device called the cavity magnetron, which generated the electromagnetic radiation known as radar. And that was certainly Britain's greatest contribution to the war effort. And then finally, the Chemical Society, Royal Chemical Society, asked him to write a review on developments in experimental nuclear fission, which he did in the winter of 1939 in his room. Britain in the winter, if any of you have been there, can be very cold. And there's not much heat. The room was 5 degrees. Water froze at night when he turned the heater off. And he didn't do much work beside that. Now, in February of 1940, he took another look at the problem, and he looked at it in the following way. I have 2 possible isotopes, U-238, U-235. I have 2 types of neutrons, slow neutrons and fast neutrons. So I have 4 possibilities. Fission of 238 with fast, fission with slow, fission of 235 with fast neutrons, fission with slow neutrons. Slow neutron fission of 238 was ruled out because it doesn't happen. Slow neutrons don't fission U-238, so that didn't work. Fast neutron fission of 238 was also ruled out because fast neutrons would scatter more than they would capture and only very slowly losing energy. And moreover, 238 releases less than 1 neutron per fission, so it can't sustain a reaction. Number 3, slow neutron fission of 235 would work for a reactor, but not for a bomb, because it takes a long time for things to happen. For fission to occur, takes times of the order of thousands of a second, milliseconds. That's, to the fission process, that's like millennia to a day for us. It's a huge long time, and the thing would overheat and just fizzle before that happened. But what about fast neutron fission in 235? Nobody had ever looked at that problem in that way before. Frisch shared his idea with Rudy Peierls. And these two gentlemen had calculated for 238 what they thought a critical mass would be. And that number turned out to be tons, way too big. But now with 235, if they could get some, and fission was the dominant process, how much uranium-235 would they need? That turns out to be a very easy calculation, at least, for Rudy Peierls. It's what's called the geometric cross-section. It's just, if fission dominates, all you want to do is calculate what's the probability of hitting a nucleus, knowing how many are in there and how they're distributed. And when they did that, the answer came out to be a few kilograms. All you need is a few kilograms, as we shall discuss at some length. You just need a few kilograms of U-235 and off you go. An atomic bomb was a real possibility. You would need a big plant to separate 235, but what was that cost compared to the financial and human cost of continuing the war, especially the possibility that Hitler got there first? So these two guys went to Oliphant, and Oliphant wrote to Henry Tizard, who was the head of the committee, the major committee in Britain that was considering the effects of science on the war. And of course, they immediately realized that what was clear to them was clear to the Nazi Germans as well. They may have thought of it first, although they thought they were first, but it was clear to them that brilliant guys like Heisenberg would come to understand it. While they thought of their idea as defensive, they thought of the Nazi idea as very offensive. Scientific facts are impossible to hide. They're the same in Germany as they are in the US, the UK, or anywhere. In Germany, Heisenberg was considering the same problem in late 39, before Frisch's idea in February 40. Meanwhile, in the US, Fermi and Szilard were busy waiting for money to buy graphite. Heisenberg wrote a memo in December 39 that energy possibility was certainly possible if a suitable moderator could be found, and building a reactor was possible, and the more 235 you could get, the smaller the reactor would have to be. Enrichment, he said, was the only way to produce a bomb. So it's likely then that he understood the use of fast neutrons before Frisch did. So not only were the Nazis in the game, they were very likely ahead. Now, finding a moderator was more difficult. Germany had no source of heavy water. The only source in Europe was Norway, a plant in Norway, as a byproduct of the electrolysis of water. IG Farben owned some stock in that, and so they sent a representative offering to buy 50 gallons of heavy water from the Norwegians. When the Norwegians wanted to know why the Germans wanted so much heavy water, there was no response. So the Norwegian answer was, sorry, no sale. The French were also aware of heavy water as a moderator, and a French bank owned the majority of the Norwegian company. So they sent somebody with money to Norway to buy, and they told the Norwegians why they wanted it, in which case the Norwegians said, you can have all you want and for free. So the French flew it off to Edinburgh and then by train and ferry to France. And that was dangerous because they had a decoy plane flying to Edinburgh, which was forced down by a Luftwaffe fighter, but of course it had nothing on board. The Russians were in the game under Igor Kurchatov, who built the first Soviet bomb in 1949. They were doing experiments. They were convinced the Americans had a big secret because there was nothing being published about fission, when in the 30s lots was being published. And they would have built the bomb had they not been busy with getting the German troops off their soil. By April of 1940, the Japanese had started a research project. Science is international, even if politics is not. In April 1940, Germany invaded Norway and Denmark. There was considerable resistance in Norway, but in Denmark, there was no resistance. The Danes did form a very significant underground resistance after occupation, but they weren't suicidal. Bohr was offered refuge in the US, but he refused and he stayed in Denmark. He had helped hundreds of people to escape from Nazi Germany, and he wanted to have time to burn all the files he had. Most of those he helped were Poles, but he also sought assurance from the government that they would resist anti-Semitic laws being imposed in Denmark. And Denmark managed to save 96% of its Jewish population. This has been compared by scholars to a country just across the Baltic, Estonia, in which 99% of its Jewish population was murdered. And lots of books have been written on the difference. Bohr also helped to save the Nobel Prize medals of Max von Laue and James Franck. Von Laue was still in Germany. Franck had fled because he was Jewish. They had been given to him for safekeeping. The Hungarian refugee chemist George de Hevesy, I mentioned yesterday, dissolved the gold in acid. It's hard to do that, but there's a special acid called aqua regia, a combination of nitric and sulfuric acids, that will do so. And so 2 jars with a black liquid stayed on a chemistry shelf throughout the war undisturbed. After the war, the Swedes recovered the gold, recast the metals, and gave them back to their rightful owners. The Norwegians, as I said, fought, and the hardest resistance was in the area the Germans wanted most, which was the hydro plant. It was the last town in southern Norway to capitulate. Heavy water production was then expanded to about 1.5 tons per year. That is until the British sent Norwegian commandos in to blow up the plant. There was an abortive attempt in November of '42, which led to the deaths of a lot of the Norwegians involved. And in February '43, a commando team blew up the plant, and that ended heavy water production, at least for a while. It took the Nazis 6 months to repair the plant, after which the Americans flew bombers over and blew it up entirely, and that was the end. Why they didn't do that in the first place and save the lives of the commandos, I don't know. But the slowest and most cautious approach was in the US. Szilard chafed under the weight, and while he and Fermi were waiting for $6,000 to buy carbon. Microscopic samples of U-235 were arriving from Minnesota, and the Columbia University was used to show that Bohr was correct and that neutrons of any energy would cause fission. Eventually, the money showed up. And it showed that carbon did not, in fact, absorb neutrons if it was pure carbon. Fission could make a useful power source in a reactor. Nobody had had Frisch's idea in the US of using fast neutrons in uranium-235. Meanwhile, politics was moving along, and Vannevar Bush, who had been president of the Massachusetts Institute of Technology, MIT, was now the president of the Carnegie Foundation in New York, was a very powerful man, and he gathered a group involving the president of Bell Telephone Laboratories, the president of Harvard, James Conant, who was a chemist, Richard Tolman, a theoretical physicist from Caltech, and Carl Compton, a physicist who is now president of MIT. They formed a science advisory committee called the National Defense Research Committee, NDRC, and they wanted a direct line to President Roosevelt. So Vannevar Bush, he's not related to any of the Bushes. I'd rather not discuss. But he appealed to Harry Hopkins, Roosevelt's closest advisor, and he got an okay. And they absorbed Lyman Briggs' Uranium Committee, which was useless. Meanwhile, the British forged ahead. The Americans were the slowest to work. And Hitler's invasion of the Low Countries, Netherlands and Belgium, led to Neville Chamberlain's resignation and to Winston Churchill becoming the Prime Minister in Britain. Frisch was continuing to work with his Clusius tube. And Peierls talked to a friend of his, another chemist named Franz Simon, who was also interested in the in isotope separation, and he thought that this thermal method of the Clusius that Frisch was investigating was not as good as regular ordinary temperature diffusion. That is, what that means is if you push a gas at high pressure against a screen that's very fine, that since the lighter molecules go a little bit faster than the heavier molecules, after the screen you'll get a slight increase of the heavy. So he took a kitchen strainer and he hammered it flat. And then he took a piece of copper screening and he hammered that flat so that it had tiny little holes. He put them together and he put sparkling water vapor against it. And now carbon dioxide in the water is much heavier than water molecules. And so the water molecules should come through first. And they did. It worked. In June of 1940, G.P. Thompson, who had his own committee, changed the name of the committee to the Maud Committee to try and hide its purpose even more. Now, the name is a bit amusing, as Lisa Meitner had visited the Boers in Copenhagen and wrote and sent a telegram to the British about her trip, saying that the Boers were okay, but very unhappy about the political situation in the world. But the telegram did not come through very well. And it said, please tell John Cockcroft, Nobel laureate in Britain, and Maud Ray Kent. Maud Ray Kent. So these clever guys said, Maud Ray Kent must be an anagram, and they tried to unravel it, and they said, oh, it's radium taken, Maud Ray Kent. A few extra letters, but... and that's because they were very much aware that the Germans wanted all the uranium and all the radium they could get, and so they thought that, okay. Well, in fact, that wasn't true. Maud Ray was an Englishwoman who had been the governess of the Boer sons and taught them English, and she lived in Kent. But nonetheless, it became the Maud Committee. She's now a very famous woman. The war had taken a very serious turn, of course, by the spring of 19, and by the end of 1940. From the September 1940, for 8 months to the May of 41, 18.8 thousand tons of bombs had been dropped on Britain in the Blitz. Okay? That, in modern parlance, is 18.8 kilotons. It killed 20,000 people in London and 23,000 people in the rest of England. 43,000 deaths. 8 months, lots and lots of German bombers, many came. One plane over Hiroshima dropped a bomb of 18.8 kilotons, one plane, one time, and killed 70,000 people instantly. Okay? That's an example of, and I can tell you that those weapons were tiny firecrackers compared to what exists on the tips of missiles today. As I said, the Germans were busy collecting radium and uranium. They did try carbon as a moderator, as well as heavy water. And this is a very interesting aside. The testing was done by a man named Walter Botha. Botha won the Nobel Prize in